universe. We've learned so much, haven't we? Tracing its origins, charting its expansion.
Absolutely. Centuries of work.
But what if I told you that, despite all that, something like 95% of the whole cosmos is still basically a complete mystery?
It's pretty staggering.
Yeah.
Our standard picture, the Lambda-Cold Dark Matter model, or CDM.
That's the one we hear about all the time.
Exactly. And it's been phenomenally successful. It lines up beautifully with so many observations. If it's a cosmic microwave background, the CMB.
The echo of the Big Bang.
Right, all the way to how galaxies cluster on the largest scales. It really is our standard model for a reason. It works.
Okay, but here's the catch, right? Its success hinges on, well, things we haven't actually found. This dark matter and dark energy.
That's the profound ignorance at its core, yes. They make up that 95%, theoretically. But direct detection, nothing definitive yet.
So this leads to a really radical thought. What if the problem isn't missing stuff?
Yeah.
What if gravity itself works differently out there on cosmic scales?
That's precisely the idea behind what we're calling the dark gravity paradigm. It's a fundamental rethink. Forget adding new ingredients. Let's tweak the recipe for gravity itself.
A completely different approach.
A completely different philosophy, really. So our mission today is to dive into this research, look critically at these alternative ideas, and see where they might lead.
Okay, let's do it. But first, to really get why someone would want to rewrite gravity, we need to appreciate just how good the standard model ЛCDM actually is. What are its biggest wins?
Well, its predictive power is just immense. With only about 6 parameters, it fits an incredible range of data, like the CMB you mentioned.
Yeah.
CDM predicts the pattern of hot and cold spots, the angular power spectrum, with stunning accuracy. Those peaks and troughs in the data, CDM nails them.
So it describes the early universe incredibly well. What about later times, the universe as we see it now?
It keeps going. It accurately describes the cosmic web, the large-scale structure of galaxies and voids.
Right, how everything clumps together.
Exactly. And things like Baryon Acoustic Oscillations, these sort of standard rulers imprinted in the galaxy distribution. Gore's EDM accounts for them. Plus, it matches the amounts of light elements like hydrogen and helium created just after the Big Bang Nucleosynthesis.
Okay, so it connects the very early universe to the large structures we see today. That's impressive.
It really is. The concordance across all these different independent measurements is why it became the standard.
But as we said, this success relies heavily on these dark constituents, dark matter and dark energy. They're not things we've, held in a lab. They're placeholders needed by general relativity to match the data.
That's the crucial point. They are theoretical necessities within Einstein's framework. Take dark matter. The evidence is indirect, but it's piled up over decades.
Where did it start?
Fritz Zwicky, back in the 1930s, he looked at the Coma cluster of galaxies and saw they were moving way too fast.
Too fast to stay together.
Precisely. Based on the visible stars and gas, the cluster should have just flown apart. He called it missing mass.
And then Vera Rubin's work.
Yeah. In the 70s, she studied how spiral galaxies rotate. Stars in the outer edges were moving just as fast as stars closer in.
Which is weird, right? They should slow down further out.
They absolutely should, if visible matter was all there was. Her work strongly implied these huge invisible halos of dark matter surrounding galaxies.
Okay, so galaxy clusters, galaxy rotation. What else?
Gravitational lensing is huge. Massive objects warp space-time, bending light. We see far more lensing in galaxy clusters than the visible matter can account for. The gravity seems stronger than it should be.
Is there one standout example of lensing showing this, like the smoking gun?
You're thinking of the bullet cluster. It's often called that.
Tell us about it.
It's actually 2 galaxy clusters that have collided and passed through each other. What's amazing is that the gravitational lensing maps showing where the mass is don't line up with where the hot gas, the normal matter, is. The gas from the 2 clusters smashed together, slowed down, and got stuck in the middle. But the lensing shows the bulk of the mass just sailed right through, almost like ghosts passing each other.
So the gravity is where the gas isn't.
Exactly. That's interpreted as the collisionless dark matter passing through, while the ordinary gas interacted and lagged behind. It's very hard to explain without dark matter.
Okay. And one more thing for dark matter?
Oh, structure formation itself, those tiny ripples in the CMB. They needed the extra gravitational pull of dark matter halos early on to grow into the galaxies and clusters we see today. Normal matter alone couldn't clump fast enough.
All right, that's a compelling case for dark matter, even if it's indirect. What about the other 70-odd%? Dark energy.
Dark energy, that was a bombshell in 1998. Two separate teams were studying type ES supernovae.
The standard candles.
Right, used to measure cosmic distances. They found distant supernovae were fainter, meaning farther away than expected, in a universe slowing down or coasting.
Fainter means farther, so the expansion is speeding up.
That was the mind-blowing conclusion. The expansion of the universe is accelerating. Within general relativity, you need something with strong negative pressure to drive that something pushing things apart.
And the simplest explanation is?
The cosmological constant. Lambda, and Einstein actually put it in his equations originally and took it out. It represents the energy density of empty space itself, the vacuum energy.
So ΛCDM, lambda for dark energy, cold dark matter. It fits the observations remarkably well.
It does.
But these dark components, they bring some serious theoretical baggage, don't they? Big questions for fundamental physics.
Oh, absolutely. Huge questions.
Yeah.
The biggest is probably the cosmological constant problem. It's been called the worst theoretical prediction in the history of physics.
Why so bad?
Because our best theory of particle physics, quantum field theory, predicts the energy of the vacuum should be enormous. Something like 10 to the power of 120 times larger than the value we actually observe for dark energy.
120 orders of magnitude off. That's not even wrong. That's fundamentally misunderstood.
Exactly. To get the small value we see, you need some unknown mechanism to cancel out this huge theoretical value to an unbelievable precision, like 120 decimal places. We have no idea why it's so small. It's a profound mystery.
Wow. Okay, what other theoretical headaches are there?
Then there's the coincidence problem. Why now? Why do we happen to live in this particular cosmic era when the energy density of matter and dark energy are, well, roughly comparable?
Because they change differently over time.
Very differently. Matter density gets diluted as the universe expands. Dark energy density, if it's lambda, stays constant. So in the past, matter dominated. In the future, dark energy will completely dominate. It seems suspiciously coincidental that we're around when they're roughly 50-50 or, 30-70.
Is it just luck, or does it hint at something deeper?
That's the question. And finally, there's the simple fact of the failure of direct detection. Decades of building ever more sensitive detectors deep underground.
Looking for WIMPs and things.
Yeah, exactly. Weakly interacting massive particles, the leading candidates for a long time. And the result has been, well, nothing. No results. We've ruled out huge chunks of the expected parameter space.
So deep theoretical problems and decades of searching yielding nothing. That's uncomfortable.
It is. And it's not just theory. Lately, some cracks have started showing up in the observations themselves. High-precision data throwing up discrepancies.
What kind of cracks?
The most famous one is the Hubble tension. It's a persistent disagreement. Now, statistically, quite significant, maybe 5 sigma.
Which is usually the gold standard in physics.
It is. It's a conflict between measuring the universe's current expansion rate, H0, using early universe data like the Planck CMB results.
Which gives about 67 kilometers per second per megaparsec.
Right. Versus measuring it locally in the late universe, using things like Cepheid stars and supernovae.
Which gives around 73.
Yeah. And those error bars don't overlap. AGM, as it stands, doesn't easily explain why these measurements disagree so strongly.
Okay, that's a big one. Anything else emerging recently? Maybe from new telescopes?
Well, the James Webb Space Telescope, JWST, has thrown up a puzzle. It's finding surprisingly many bright, massive galaxies very early in the universe's history.
Impossible early galaxies, I've heard them called.
Kind of, yeah. Some appearing when the universe was maybe only 3% of its current age. Standard CDM simulations struggle to form such massive galaxies so quickly. It suggests maybe structure grew faster than we thought, or our galaxy formation models are missing something.
Interesting. And what about dark energy itself? Is it definitely constant?
That's being tested too. Recent results from the Dark Energy Spectroscopic Instrument, DETI, hinted, and it's still tentative, maybe around 3 sigma significant.
So not definitive yet.
Not yet, but suggestive. They hinted that dark energy might actually be evolving over time, changing its strength. If that holds up, it would rule out the simple cosmological constant, lambda.
Which would be huge.
It would open the door wide for either more complex dark energy models or modifications to gravity.
Okay, so you've got these deep theoretical issues, like the cosmological constant and coincidence problems, plus null detection results, and these growing observational tensions.
Right. The Hubble tension, the early galaxies, maybe evolving dark energy.
It really does build a strong case for, at least looking beyond the standard model, which brings us back to dark gravity.
Exactly. It sets the stage perfectly. The core idea of modified gravity is simply this. What if the effects we attribute to dark matter and dark energy aren't caused by new stuff, but by gravity itself behaving differently on large scales?
So instead of adding things to the right side of Einstein's equations, the matter and energy side, you change the left side, the gravity side.
Precisely. You rewrite the laws of gravity. The dark universe then becomes, in a sense, an illusion caused by using the wrong gravitational theory.
That is a fundamental shift in thinking. So how on earth do you even start rewriting general relativity? What are the main ways people are trying to do this?
Oh, there's a whole zoo of ideas. It's a really active field. One major category is what we call geometric modifications. These stick with the basic idea that gravity is geometry, but they change the mathematical rules.
Okay, like what?
The most famous and maybe simplest is FR gravity. Instead of just the Ricci scalar r in the equations, which GR uses, you replace it with some more complicated mathematical function of r, hence FR.
And what does that do?
Depending on the function you choose, it can mimic dark energy, causing cosmic acceleration without needing a cosmological constant. And what's really interesting,
Yeah.
some recent studies using the latest supernova data and results from DKI are claiming that certain types of FR models actually provide a better fit to the late universe expansion data than standard CDM.
Better. Significantly better.
One paper even claimed a 4 sigma preference over CDM. Now, that's still being debated, very heavily scrutinized.
Of course.
But if true, it would be a massive deal. It would strongly suggest GR needs modification.
Wow. Okay, any other geometric approaches?
Yes, there's FQ gravity, which is
Oh.
based on something called non-metricity instead of curvature. It's mathematically different from FR. It's very flexible. You can get SCDM behavior or something totally different.
But. I sense a but.
But
Yeah.
this flexibility comes at a cost. Many FQ theories, when you look closely at their mathematics, suffer from serious problems. Theoretical pathologies, we call them.
Like what?
Things like ghosts, fields with negative energy that make the vacuum unstable, basically blowing up the universe, or strong coupling issues, where the theory breaks down and loses predictive power. So while promising on the surface, FQ faces big theoretical hurdles.
Okay, so tweaking the geometry is one way. What about more radical departures, where gravity isn't fundamental?
That leads us to emergent gravity. The idea here is that gravity isn't a fundamental force like electromagnetism, but emerges from something deeper, maybe related to quantum information or thermodynamics.
It's like temperature emerges from molecular motion.
Kind of like that, yeah. The most well-known version is Eric Verlin's entropic gravity. He proposed gravity arises from changes in information, specifically entanglement entropy, in some underlying quantum system.
And how does that relate to dark matter or dark energy?
In Verlin's picture, what we perceive as dark matter is actually an elastic response of spacetime itself when normal matter displaces the background dark energy entropy. It's not a particle. And intriguingly, it naturally connects to the MOND acceleration scale.
MOND, modified Newtonian dynamics, another alternative gravity idea.
Right. Verlin's theory sort of naturally reproduced that characteristic acceleration scale, linking it to the Hubble constant.
That sounds really elegant. Conceptually, how does it fare against observations?
It's mixed. It had some remarkable early success fitting weak lensing data from thousands of galaxies, apparently without needing any free parameters to tweak.
No tweaking. That's impressive.
It was.
Hmm.
But it struggles significantly with other observations, like the dynamics of dwarf galaxies, and especially with things like the bullet cluster, explaining that separation of mass and gas is very difficult if there's no actual dark matter particle.
Right, the bullet cluster strikes again. Okay, what else is out there? Extra dimensions. That always sounds like science fiction.
Well, it's serious physics. Extra-dimensional theories propose our universe, with its 3-space and 1-time dimension, is just a brane, like a membrane, floating in a higher dimensional space called the bulk.
Okay.
A really interesting modern example, which is getting attention because it comes from string theory, is the dark dimension scenario.
String theory predicting something testable. That's news.
Sort of, yeah. It arises from consistency conditions in string theory called swampland conjectures. It predicts that just one extra dimension, is much larger than the others, not curled up super tiny, but about a micron in size.
A micron. That's 10 to the 6 meters. Tiny for us, but huge for string theory.
Exactly. And in this scenario, dark matter isn't a new particle in our dimensions. It's massive versions of the graviton, called Kaluza-Klein or KK gravitons, that can travel in this micron-sized extra dimension.
So dark matter is basically just gravity leaking into this tiny extra dimension.
In a sense, yes. It unifies dark matter with gravity. And what's really neat is that it naturally connects the observed dark energy density to the mass scale of these KK graviton dark matter particles. It might potentially solve the coincidence problem.
That is elegant. Are there older extra dimension ideas?
Oh yes, the DGP brane world model was an important earlier attempt to explain cosmic acceleration using extra dimensions. The dark dimension is kind of the latest string theory motivated version.
Okay, one last category, something really new.
Very new, yes. Quantum classical hybrids. These are just starting to be explored. They look at how classical gravity, like spacetime, might interact with quantum matter fields in unexpected ways. There's a proposal by Jonathan Oppenheim called the post-quantum theory of classical gravity. It suggests spacetime is fundamentally classical, not quantum, but it's inherently noisy or wobbly.
Wobbly spacetime.
Yeah, random fluctuations. The idea is that these inherent jitters in classical spacetime itself could mimic the effects we attribute to dark matter and dark energy. It's extremely speculative, not even peer-reviewed yet, I believe.
Wow.
But it shows people are really thinking outside the box, questioning even the need to quantize gravity itself.
What a landscape, from tweaking geometry to emergent phenomena, extra dimensions, even wobbly spacetime. But surely, any of these radical ideas has to pass some basic tests just to stay in the game.
Oh, absolutely. There are critical universal challenges. First and foremost, solar system tests.
Making sure planets still orbit the sun correctly.
Exactly. General relativity works incredibly well within our solar system, tested to amazing precision. Any modified gravity theory must have a way to shut off its modifications in high-density environments like ours. It needs a screening mechanism.
So it looks like GR where GR is known to work.
Precisely. If a theory can't do that, if it messes up planetary orbits or the moon's motion, it's dead on arrival. Fatal.
Okay, solar system survival is rule number 1. What else?
Theoretical stability. The theory has to make mathematical sense. It can't have those ghosts we mentioned, particles with negative kinetic energy that would cause the vacuum to instantly decay.
Right, no universe-destroying instabilities allowed.
And it shouldn't suffer from strong coupling, where the interactions become infinitely strong and the theory loses its ability to make predictions. Many otherwise interesting ideas, including some FQ models, have sadly failed these theoretical consistency checks.
So, pass the solar system test, be mathematically sound. Then what? How do we pit these theories against the cosmos? Where's the real showdown with data?
The ultimate arbitrator is observation, of course. And the cosmic microwave background is probably the single most powerful data set we have. It's the highest hurdle.
Because a CDM fits it so well.
Exquisitely well. Any contender, any dark gravity model, absolutely must be able to reproduce that detailed pattern of peaks and troughs in the CMB power spectrum. And so far, no modified gravity model has shown it fits the CMB data alone significantly better than CDM. That's a major challenge.
Okay, CMB is tough, but it's a snapshot of the early universe. What about probing gravity more recently, using how mass bends light?
Right, gravitational lensing is super powerful because it traces all mass, visible or not. And this brings us back to the bullet cluster challenge.
The colliding clusters again?
Yes. That separation of the gravitational signal from lensing and the baryonic gas signal from X-rays is just really, really hard for most modified gravity theories, especially MOND-like ones, to explain.
Yeah.
How do you get enhanced gravity centered where there's hardly any normal matter?
It really does look like collisionless particles sailed through.
It's the interpretation that fits most easily, certainly. But lensing isn't just about extreme cases. Weak lensing surveys are mapping the subtle distortions of millions of distant galaxy shapes by intervening mass.
Like the dark energy survey, kids, and upcoming ones.
Exactly. Euclid, the Vera Rubin Observatory. These will create huge maps of the invisible mass distribution. They can test if galaxies simply trace dark matter halos, as in ΛCDM, or if the relationship between light and mass follows the different, often scale-dependent rules predicted by modified gravity.
So lensing maps are a key battleground. What about the universe's expansion and growth, especially late time where ЛCDM seems to have tension?
Precisely. The late-time universe is where dark gravity models often have the most wiggle room and are most competitive. We can probe the expansion history using supernovae and BAO.
And you mentioned some FRR models claim a better fit there.
Yes, that's where those claims of better statistical fits are coming from. Ongoing surveys like DDI will measure the expansion history with unprecedented precision, really putting these models to the test.
And not just expansion, but how structures grow.
Right, the growth of structure. How fast did galaxy clusters and filaments assemble over cosmic time? Modified gravity can change the strength of gravity on large scales, potentially speeding up or slowing down structure formation compared to ACDM. Upcoming surveys aim to measure this growth rate to percent-level precision.
That sounds like a very sharp test.
It really is. Comparing the expansion history to the growth history is a powerful way to distinguish GR-based models from modified gravity.
Okay, observations of the cosmos.
Yeah.
What about direct searches for new physics, maybe in labs? Could that help?
Potentially, yes. The search for new forces and particles is relevant. For example, fifth force searches.
Looking for tiny deviations from gravity at short distances.
Exactly. Using incredibly sensitive torsion balances or atom interferometers, physicists are looking for new forces that might only operate over, say, sub-millimeter distances. This is critical for theories like the dark dimension scenario.
Because it predicts that micron-sized extra dimension.
Precisely. If a new force showed up at the micron scale, that would be direct, smoking gun evidence for that specific kind of dark gravity model.
And particle colliders, like the LHC.
They play a role too.
Yeah.
If a modified gravity theory involves new fields or particles that interact, even weakly, with standard model particles, the LHC might have produced them. The fact that we haven't seen strong evidence for such new particles puts constraints on certain types of modified gravity models.
So many angles. It really feels like the next decade or so could be absolutely transformative for cosmology.
I think so. It's a pivotal moment. If we step back and look at the big picture,
Yep.
KCEM is still the reigning champion. Its successes are undeniable. But it's a champion built on, well, admitted ignorance about 95% of reality. It's haunted by these theoretical ghosts of fine-tuning and coincidence. And now, it's facing increasingly sharp challenges from observations, especially these tensions between the early and late universe.
And into that breach steps dark gravity in all its diverse forms. It's such a radical alternative solving the mysteries, not by adding more unknowns, but by fundamentally rethinking gravity.
Yeah, and we've seen the variety. You've got geometric theories like FR, maybe fitting some data better, but facing theoretical questions. You have emergent gravity, beautiful ideas like Verlinde's, but struggling with some key observations.
And things like the dark dimension, coming straight out of string theory with very specific testable predictions like that micron-scale force.
Each has its appeal, each has its hurdles. It's a dynamic, exciting, and frankly difficult field right now.
The future really does seem to hang in the balance. This flood of new data coming from telescopes like Euclid, Rubin, DESI, it feels like it has to break the deadlock one way or another.
Either the tensions will resolve within ACDM, maybe pointing to subtle observational effects we missed, or subtle tweaks to this standard model,
Right.
or we'll get the first really compelling evidence that general relativity isn't the final word on gravity, that we need a new theory.
Which leads to maybe the biggest question of all for you listening. If a theory does emerge, one that convincingly explains cosmic acceleration and galaxy rotation without needing dark matter or dark energy just by rewriting gravity, what does that actually mean for how we understand reality, for the nature of space, time, and the cosmos itself?
It would be a revolution on par with relativity and quantum mechanics, a fundamental shift.
So what stands out to you from this deep dive? It's a universe of questions, but also buzzing with potential answers. A fascinating time to be exploring the cosmos. Keep looking up.